Hello, and welcome to another lesson about formal language theory. In previous videos, we have talked about how any language that can be produced using a regular grammar it can be called a regular language. So notice that this definition says that any language that can be generated by a regular grammar is also a regular language, and that's because anything that can be written as a regular grammar can also be written as a context-free grammar, as a context-sensitive grammar, or as an unrestricted grammar. You can rewrite them in more complicated forms, but what's important about a regular language is that it's a language that you could choose to represent with a regular grammar if you could figure out how to do it. So this is what this video is going to be about, and the next couple videos will be about the properties of these languages. Now, because of what we said in the last video, you also know that anything that can be generated by a regular grammar can also be generated by a finite automaton. So this also means that any language that can be generated by a finite automaton is also a regular language. But we're going to take it from the perspective of regular grammars. We're just going to talk about regular grammars rather than about automata. And what we're going to do is we're going to go through various properties, which you can see listed all together in your book, and talk about why those must be properties of regular languages given our definition of what a regular grammar is. All right. So our first property is not, it doesn't really feel like a property. It feels more like just a statement about the world. But when you see them listed all together, it makes a little bit more sense why we might want to state this explicitly as a property. And this property is that the empty set is a regular language. Now, how you lay out this language can be a little bit confusing. But let's first look at the things that are required for a regular grammar. So for any grammar of any language, we need a root node. We need to have a set of terminal nodes. We need to have a set of non-terminal nodes, and we need to have a set of rules, right? So we know that we need to specify a root node. So let's just label this root node S, because it doesn't matter what we call it, really, right? So that's going to be our root node. What does that also mean? It means that our set of non-terminal nodes will at least have to include S, right? We might have to add more, but we know that S is a member of our set of non-terminal nodes. Now we ask, if a language contains no strings, can it have any terminal nodes? The answer is no. So our set of terminal nodes is going to be empty. It's the empty set, which is allowed, right? All that we care about is that there's a set here, right? We don't care what's in the set, right? And there is a set, it's just empty, right? As it turns out, this is going to be the only member of our set of non-terminal nodes. And then we need a set of rules, right? And our set of rules has to generate absolutely nothing, right? And so the easiest way to have a set of rules that generates absolutely nothing is to just not have any rules, right? So we have this sort of non-terminal element that's sitting in there and not doing anything, and that's just because of our definition of a grammar and how we have to do our grammar. But essentially all that this really is saying is that you don't do anything and you have a regular language. And we know that this is a regular language because it's a well-formed grammar, right? It's a grammar that works, and none of your rules are of any form other than or, right? So there's no rule in here that has another form than this, right? We don't have any rules in there, so they have to, be appropriate to those definitions. So this is a regular language which has no members, right? I want to take a note briefly to say that the language that is the empty set is not the same thing as a language that has nothing in it but the empty string. Now, if we're actually talking about like speaking a language, right, then it would be, you would speak it the same way, but its formal definition is slightly different, and you can tell that because you actually define the language, the grammar of your language will look different. So let's just talk about how we would build the grammar for this language, the set containing the empty string language. So first of all, we have to have a root node, which we'll call S. We have to have a set of non-terminals, which will be the set containing S. And we have to have a set of terminals. Now we might list the empty string in here. I'm going to do that. Different people treat the empty string differently, but this is going to be our terminal, right? Because you actually are producing a thing. It's just silence, right? It's just nothing. It's just that you're producing nothing. It's like producing zero, right? And so your rule, you are actually going to have a rule in this version, which is that S goes to the empty string, right? So this is still a regular language. It still falls into the definition of a regular language, but it's not exactly the same as the language that is the empty set. All right, so that's our first property, that the empty set is a regular language. What's our second property? This one is a little more complicated. This one states that for any string X that's a member of sigma star, we'll talk in a second about what this means, the set containing X is a regular language. So we have talked about this sigma star before in a sort of vague way. We're going to define it more strictly right now. So sigma, remember, is the symbol we use for our alphabet. When we put this little star up here, this is called the clean star. It's read clean, not cleany or whatever. It's read clean star. And it means that this is the set of all possible strings over the alphabet sigma. So this means the set of all strings that you can create using your alphabet. So if you have an alphabet that is 1, 0, 1 and 0 are your choices, your set of all possible strings over the alphabet, which is called your clean closure, or there are other things you can call this, but this is the set of all possible strings over the alphabet sigma, is the empty string 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, so on and so forth to infinity. So what does it mean that X is a member of this set? This basically means select any one string made up using that alphabet and put it in a set. Right? So long as you're selecting just one string and you put it in a set, that set is going to be a regular language. So how do we show that this can always be a regular language? Now let's think about breaking up a word, right? So if we have the string A, B, something, 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 and C, right? So that's going to be the string that we're going to assemble is A, B, something, 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 whatever we want in here, and it's going to end in a C. What can we do? We can have our start symbol here. This breaks into state add a B. This is the add a B state. Right? And all that this state is going to do is split into another state, which is going to be an add an F state, or add a Q state, right? You can just add whatever you want with each state and just keep naming the state a new thing for every symbol that you're making until finally you get to add a C state, and that breaks down just into C, right? And so even if you're adding the same symbol multiple times, you could have a different rule. So let's say you want to have A, B, B, something, 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 C, right? We would say add B1, and then we would have, B prime, which breaks into something and something else, right? Right? So on and so forth. So you can just create like one non-terminal for every terminal node you have. For every time you add another non-terminal node, you can add, or every time you add a terminal node, you can add a new non-terminal for that. So S would be, your start state would be S. Your set of non-terminals is the set of things Y, such that Y is a non-terminal in string X. And then your set of non-terminals, I'm not going to define explicitly. I'm just going to put in words that you have a non-terminal for each instance of each terminal in X, in string X, right? And then you have a rule for building each non-terminal. Right, and all of these rules will be appropriate for regular languages, right? You have a non-terminal or a terminal followed by a non-terminal, a terminal followed by a non-terminal, which is fine, and then eventually you'll have one non-terminal that just becomes a terminal, right? And so this is going to be a regular language. We don't care what the string that we select is. We know that we can create a regular grammar for that string. All right, so in the next couple of videos, we'll talk about different properties of these languages, so tune in for those.